Okay, so yesterday we set up the kind of machinery of post-Minkowskian theory and a way of approximating solutions of Einstein's equations. And now I want to get down to one of two specific regimes for dealing with these solutions. As we discussed earlier, there are two fundamental regimes in space-time, or in space, that you need to think about: the near zone within one gravitational wavelength of the source, and the far zone out where you start to see the wave-like nature of the field that is being produced by the source. And so the last 6 lectures of this course will be split roughly in half. First half talking about the near zone, the second half talking about the far zone, where the waves and where LIGO reside. But we do need to talk about the near zone because that's where we can analyze and calculate the motion of the sources that are producing gravitational waves. So we need to work there as well. And what I want to do in this first 3 lectures is focus on near zone physics with this post-Minkowskian approach. But to keep things simple and not to get too crazy, we're just going to work at first post-Newtonian order. In fact, these days, we now have these approximate solutions of Einstein's equations for things like compact binary systems, all the way up to something like 3.5 and approaching 4th post-Newtonian order, including the effects of spin and all kinds of higher order corrections. But I won't say very much about that. I might, at some point, insert a slide from some other talk to show you what the formulas look like. Each formula, takes 3 or 4 pages of a PhysRev article just to list all the terms. But you look at the formula and you say, okay. But I hope that working just at first post-Newtonian theory will give you some feeling for how these calculations might go. But even at post-Newtonian theory, I'm going to spend some time talking about the actual phenomena that are important at that level. Perihelion advance of Mercury, the deflection of light, gravitational lenses, and so on. So there's a lot of physics that we can discuss, even working at 1 PN order. So first I need to kind of just introduce the fundamental variables associated with the matter that we'll be using. So last time I defined the density, the rest mass density of matter. That's a physically measurable quantity. It's an invariant quantity because you measure it in a local inertial frame, momentarily co-moving with the element of fluid you're looking at, and you simply measure the mass density of that fluid, the total mass divided by the volume. Okay, so that's an invariant quantity by its very definition because it's defined. It's defined in a specific frame attached to the matter. So it's a scalar quantity, rho. In that same frame, you measure the pressure on your fluid, you measure the internal energy density, but this is a variable that is often used in post-Newtonian physics. We talked about the energy density in your fluid, all the various forms of energy. Can you see this over there? No, so we talked about the energy density. Pi is simply the energy density divided by the rest mass energy density. So it's basically energy per unit rest mass, roughly speaking. So it's a dimensionless quantity, energy divided by energy. So it's sort of the fraction of the total energy density that's in all these other forms of energy, not rest mass. Okay? It's just a handy variable to use. I think it was first introduced by Chandrasekhar, actually. And our fluid element, of course, has the same 4 velocity as our local inertial frame because we're co-moving. And then in the coordinate system, you can define what that is. So it's a 4 velocity, and you can factor out the U0, and then you just have 1 and V over C. I've also written it over here in a slightly different form. The 4 velocity, is the rate of change of x, the 4 coordinate, with respect to proper time. And I can factor out this gamma, which is just proper time divided, it's basically time divided by, proper time divided by the coordinate time. So it's just calculated in terms of the metric, contracted on the 4 velocity. So this is just g alpha beta dx alpha dx beta divided by dt squared, and it's to the -1/2. So there's an overall factor and a c and a vj. Okay? So those are two equivalent expressions for the forward velocity. But it turns out that in post-Newtonian theory, when you start going beyond Newtonian theory, there's a different density variable, another one, that is much more useful than the physically measured rest mass density. This is a physically measured quantity, it's a scalar, but it turns out to be much more handy to use a different density that we call rho star. It's constructed from rho, but you multiply rho by the square root of minus g, g is the determinant of the metric, and by the 0th component of the forward velocity of your fluid element divided by c. So this is no longer a scalar quantity, it's no longer a frame invariant. You've got a single component here, and you've got a density here, so it transforms in some strange way. But we don't care about transforming it, right? We are working in a fixed coordinate system. We've chosen our harmonic coordinates, so we've given up all these issues of general covariance anyway, so why do we care if we don't use something that's an invariant? We've given up invariance. We're working in a set coordinate system, so let's use something that behaves nicely in that coordinate system. And this rho star behaves very nicely, because you remember the conservation of baryon number said that there's this current, the baryon number current, that is conserved, because we know baryon number is conserved. And then if we just multiply by the mass per baryon, which for hydrogen is so many grams per baryon, depends on the chemical composition of our fluid, then we get a conservation law of this rest mass density times the forward velocity has 0 divergence. That is a covariant statement using our physically defined rho. So it simply expresses the conservation of baryon number and the fact that the chemical composition doesn't change, so the mass per baryon is the same. But you can convert this, if you remember what the divergence is. The divergence of any vector is equal to 1 over root minus g times the partial derivative of root minus g times the vector. So in this case, this partial derivative, this divergence becomes 1 over root minus, and this is 0 in this case, so it's d0 root minus g rho u0 plus dj root minus g rho uj. And that vanishes. Remember, uj is the same as u0 times vj, where v is the ordinary velocity, right? So I've taken this covariant divergence of rho u alpha, written it out in terms of coordinates. The first term is this, the second term is this, but notice the second term is the first term just times vj. And so this expression just looks like a continuity equation, our old friend, the Newtonian continuity equation, but not for rho, but for this combination. d0 rho star plus the ordinary divergence of rho star times v vanishes. So the conservation of baryon number gives us a continuity equation, not for rho, but for this special rho, this rho star. But this is extremely useful because now if we define all our potentials and all our variables using this rho star, we can adopt all the rules of the road that I showed you in the very first lecture for taking time derivatives and manipulating things, as long as we define things with this rho star. Okay? So this is sometimes called the conserved density. This is the proper density, the real measured one, but this one is conserved because it satisfies this nice continuity equation. So again, it's just a definition, it's just a choice, but it's one that turns out to be extremely useful. And so you'll see from now on, sort of all our potentials, the Newtonian potential, all the various potentials and things we define will be defined using rho star. We're also so these are the kinds of variables we'll adopt. We're going to define this new rho star. And then we're also going to assume that the systems that we work with have low velocities. Velocity is small compared to the speed of light. Now this makes sense, in fact, for the kinds of physical systems we're interested in, because we've already assumed that Gm over r c squared is small compared to 1. That's our weak field assumption. That's the idea that H, our fields are going to be small compared to unity. But for typical systems of interest, like binary systems, stars, any kind of body system that's bound by gravity, Gm over r is comparable to v squared. It's just a virial theorem, right? It's just the kinetic energy has to be comparable to the potential energy if you're in a bound system. So v squared over c squared is actually going to be comparable to this quantity. So if this is small compared to 1, then we expect v over c to be small compared to 1. In fact, these typically are of the same order of magnitude. In fact, you can go one step further and argue that typical energy densities are small compared to rho, to the mass energy density. So this is also comparable to pi over c squared. Well, there's a c squared there already. Pi is already dimensionless. And if you really want to talk about bound systems, this gravitational potential has to be comparable to the characteristic pressure in the body. Remember, because it's pressure, the gradient of the pressure that balances the gravitational force, so P and the potential had better be comparable. So this is also comparable to P over rho c squared, again, a dimensionless quantity. So all four of these things are comparable to each other in the characteristic systems that we'll be treating. And they're all going to be assumed to be less than 1, and we're going to collectively label all of these quantities, all of these small quantities, with the label epsilon. Okay? So epsilon is to be a useful parameter just to express orders of things. It'll be of order any of these things. So V over C itself will be of order epsilon to the 1/2, for example. So, yeah. Well, sure. If you had a black hole moving at the speed of light, scattering off another black hole, that would be a regime where slow motion assumption would not work. The trouble is, how do you get a black hole moving near the speed of light? It interacts with other objects via gravity, and it's tough, for gravity to boost things up to the speed of light, except maybe when they're very close together. But when they're close together, the weak field assumption breaks down. So again, practically speaking, it's very difficult to imagine a system working under gravity reaching the speed of light in a weak gravitational field. Doesn't mean to say you couldn't imagine a civilization boosting a black hole to the speed of light and shooting it around, but
So they always go hand in hand. Does well, always imply the other?
Well, not always. As I said, you could imagine situations where they don't, but for the kinds of systems that we deal with that are gravitationally bound and where the movement is produced by the gravitational field itself, internal to the system, they tend to go hand in hand. I mean, it's not a rigorous statement, but if you just think about the typical systems you want to look at, these relationships generally occur. So with this assumption, then we can think about the sizes of the quantities that are going to enter our problem. We are going to deal with our field H, the quantity we defined early on using the Gothic metric. We need to deal with the stress energy tensor of matter that is written out over there. So one thing you can say, though, is that we know what T00 is. It sort of looks like the density. T0J looks like a momentum density. But the point is this has one index, so there's got to be a Vj in there somewhere, right? There's nothing else that has a one index in our problem, so there's got to be a Vj here relative to that. So clearly the ratio of these two things is going to be of order V over C. So the jth component of T is going to be smaller than the 0, component by a factor of roughly V over C. And similarly, Tjk, there it is over here, it's going to have factors of Vj, Vk. Or here you've got a factor of P, which is also small, by the same epsilon, V over C squared. So this compared to that is roughly of order v over c squared, or of order epsilon. So this hierarchy of components, then, it's important to keep this in mind as we work out what these fields look like. And similarly, since this is roughly speaking is the source of that, then it stands to reason that the ratio of these fields has the same hierarchy of terms. Okay? So the next question to ask is, we would like to ultimately get the metric. We need the physical metric to do physics, right? G0, G alpha beta, that's what we need. The route to get there is to first calculate the H's using our Post-Minkowskian theory. From those H's, construct the G's. Now, if we want to go beyond Newtonian theory to first post-Newtonian order, we should ask ourselves, well, what do we need to calculate? How accurately do we need to know things to get all the first post-Newtonian corrections to normal Newtonian theory? And one way to see what you need is to go back to the simplest way of thinking about the motions of particles in a curved space-time, and that is to look at the action for a geodesic. So the action for a particle moving around in a curved space-time, it is simply the integral of proper time between two fixed points on the path of the particle. It's constant, it's just for conventions. Proper time, of course, can be written in terms of, say, coordinate time between the 2 points by sticking in the relationship between proper time and coordinate time. It's just this, where r is the location of the particle and t is coordinate time, and there's the metric. Okay, there's proper time written down there. It's the same. That's the same factor, proper time divided by coordinate time. And let's expand this out in terms of all the different components, 0, 0 component, and so on. So if you look at the 0, 0 component, we'll see shortly. We'll get there in a minute, but I think it's pretty fair to say you probably already know that the lowest order G00 is -1 plus 2 times the Newtonian potential. We'll derive it directly in a minute, but it's pretty well known. So, and don't forget the minus sign here to make everything positive. So the 0, 0 component will be 1 minus 2u over c squared minus the next order correction in G00. Right, this is the lowest order term, what we call the Newtonian term. This will be the next correction. And then there's the term when we have 1, 0, and 1j. That occurs twice, so there's a factor of 2. That's 1, that's Vj, and we get G0j. And then there's the terms when both of these are spatial. So we have of course, at lowest order, Gij is what? For the Minkowski metric, what's Gij? Delta ij, a Kronecker delta. So the first term, the leading term in Gij just gives v squared over c squared. Okay, and then, but then there'll be a correction term to that that'll contract with Vi, Vj. So this is sort of the generic structure of this action that you would use to get your equations of motion for a particle. You vary this action with respect to, alternative paths between 1 and 2, and that gives you Euler-Lagrange equations that you then use to generate the equations of motion. And so the question is, what do we need in order to, what appears in this action that is of interest? Well, the first thing is, this is of order epsilon, right? This is our statement, gm over rc squared. This is of order epsilon, so that's the lowest order. And so is this, v squared over c squared. And if you take that part, forget all the other stuff, and simply expand the square root, you get u plus 1/2 v squared. Plus a constant that, of course, is irrelevant. Well, u plus 1/2 v squared is simply the action for Newtonian gravity, right? So knowing the metric, knowing G00 to epsilon, the lowest order, and that's all, and just knowing that the Minkowski metric is the lowest order term, that's enough to give you Newtonian theory. You can get the equation, you can get Newton's equations from just that action, right? vary with respect to v, vary with respect to x. The Euler-Lagrange equations gives you dv dt is grad u. You're there. So Newtonian theory tells you to get Newtonian theory, you need the G00 to order epsilon, and that's it. You're done. Now, what we want is post-Newtonian theory, which means we want to go to order epsilon squared. So that tells us that we need to know this guy to order epsilon squared. We need to know the next correction in the 0, part of the metric. This we need to know to order epsilon squared. Also, well, v is of order epsilon to the 1/2, but then G0j, it looks like it's going to be order epsilon to the 3/2. It's a metric component, so it's got to have m over r in there somewhere. It's got to be like a potential. And it has an index, so there's got to be a v inside there. And that's epsilon to the 3/2. So it tells us we need to know G0j to order epsilon to the 3/2, so that when you multiply by v, you get a post-Newtonian correction. And then finally, here, if we want to get a contribution at order epsilon squared, well, this is already of order epsilon, so we only need to know Gij to order epsilon. So that then tells us what we need to do. We don't need to calculate Gij to order epsilon squared. I mean, you can, but you don't need it. You'll need it if you want to go to second post-Newtonian order, but for one post-Newtonian order, you just need to get this to order epsilon. This one, you need to get to epsilon and epsilon squared, so you really need to go to the next order to get what you need. G0j, you just need it order epsilon to the 3/2, and it's easy to see that's the lowest order you can possibly have. So you just need the first order contribution to G0j, and that's all you need. And it's clear then what you need if you want to go to 2pn order, you need this epsilon 3, 5/2, and 2. To go to 3pn order, you need 4, 7/2, and 3, and so on. Just to higher and higher order, this tells you what you need to do. But what this tells you, among other things, we talked about taking our wave equation for h, and we had to iterate, plug h equals 0 on one side, get a solution, plug it in, and keep going. Because this thing involves going to epsilon squared, which also means going to order g squared, because epsilon squared can mean this all squared, but it can also mean that all squared, which means 2 powers of g, so we need to get a second iteration of the relaxed Einstein equations. So a first iteration, what's often called linearized theory, isn't good enough to get our answer. We have to iterate twice, but if we're clever, all we need to do is iterate twice enough to get the G00 stuff. You can iterate twice and calculate higher order corrections here, but we don't need them for 1pn order. So if we're careful, we can save work, but we do have to iterate twice. Solve once for h, get that solution, and plug it back into the right-hand side and solve again. Okay? Any questions so far? Yeah. Sorry?
Can you explain this last part again?
This one? Two. Because if G00 has contributions that order epsilon squared, that means it could have contributions that look like, that are maybe a potential with a v squared inside it, like a potential generated by kinetic energy. So that would be like a product of these two things, right? But you can easily see that to get epsilon squared, you might have something that involves a potential generated by the potential itself, which would involve 2 g's. Well, one iteration for h just gives us 1 power of g. So we have to be open to the fact there might be terms that involve 2 powers of g. Maybe they won't occur, but we don't know that until we do the calculation. So we really have to check the second iteration to be sure. But of course, we're not calculating g, the metric, directly. We're calculating h, and there's a complicated relation between the two, so it's worthwhile actually figuring out what that relation is. It'll help us to save us work if we know what we need in terms of h to get what we need in terms of g. And so you remember the definition was that h let me do it this way, that the Gothic metric, G alpha beta, was equal to eta alpha beta minus H alpha beta. And remember, this was equal to the square root of the determinant of the metric times the metric inverse. But it's clear that you can, since H we expect to be small, you can expand these things in powers of H to get a relationship between the ordinary metric and H. You have to work out the determinant of the metric, and it's useful to note that root minus G is equal to the, and I'm going to get this wrong, it's the determinant of the Gothic metric to some power. You can figure out the power, I can't remember. But you have to work out, remember, the determinant of an inverse is the inverse of the determinant, and so on. So it's just a little bit of matrix algebra you can work out. But using all this machinery, you can then find a series expansion, a power series expansion for the downstairs metric in terms of these H's. And they're shown here. So here's the minus G. The determinant of the metric is 1 minus H. This is a trace of H. The spatial, this is the trace of H. The trace of H using the Minkowski metric. But then there are higher order terms, quadratic terms, then you can keep going, cubic terms, and higher order. So you can do this in a series expansion. You can fire up Maple and do all the matrix algebra and work it out. And then the metric itself is the Minkowski metric at lowest order, plus H alpha beta minus something involving the trace of H. If you've had courses in GR before, you'll recognize this as what's sometimes called the trace reversed H. So there's how it appears. But then there are quadratic terms in H. Okay? And then cubic terms and on and on. If you're going to higher orders, you go to higher orders. But now we're working to post-Newtonian order, and remember, we don't need all the information that's included here. We only need G00 up to order epsilon squared. So that really says we only need so for example, we need H00, where are we? So we need H00. Here, indices can be raised and lowered using the Minkowski metric. That's just a rule in this whole game. So I've made these indices upstairs because that's what we calculate. So, so there's a 1/2 here because there's an H00 here and an H00 in there also, in that trace. So you get that. You get an HKK, that comes from the spatial part of that trace. And you get some other terms. And you remember, this is smaller than that by a factor of epsilon to the 1/2. And this is smaller than that by a factor of epsilon. So this is already a post-Newtonian term. This will include Newtonian plus post-Newtonian corrections. In all this garbage, when you put 0, for the indices, in all these quadratic terms, the only thing that survives is H00. And the 3/8 just comes from adding up various terms. That's because the spatial indices is smaller than H00, and so all the various spatial bits that come in here, you can throw away because they're higher ordered. So to get G00 to post-Newtonian order, we need H00, including the corrections to that, and that's where we have to iterate twice. But this is already post-Newtonian order. We just need the lowest order bit. And this is quadratic in H00. So for this, we can just plug in the Newtonian result because it's squared. Similarly, for H0J, I mean, it's really just that, H0J, with a minus sign, because when we raise the 0 index, you get a -1. So you just need the lowest order result there. That's already order epsilon to the 3/2. Then there'll be higher order corrections. The spatial part is easy. We get it for free. If you look at the spatial part of this thing, remember all the spatial indices here are of higher order. The only thing that it contributes is H00 multiplying the Kronecker delta from here, right? So once we get H00 at Newtonian order, we get GJK for free to the order we need. So really, all we have to worry about are this, but we have to iterate twice to get the correction in there, to get this to lowest order, and to get H0J. Those three things. Once we have that, we have enough to get the 1PN metric. Okay, well, let's try to see how that might go in some rough sense. So here are the equations that a truncated version of the equations that I showed last time. H00, remember, was an integral of tau 00 over x minus x prime. Tau, you remember, is the stress energy tensor of matter plus the Landau-Lifshitz plus the harmonic pseudotensors with a minus g in front. And plus there's a post-Newtonian correction that involves 2 time derivatives of the superpotential, so we need to include that. That's a 1PN correction to the lowest order term. H0J is given by this thing using tau 0J, and then there are higher order corrections there, but that tells us we just need this leading term, so forget all that other junk. And similarly, HKK, here I've taken the spatial trace because the tensorial part doesn't appear there. It's of higher order. It contributes, Hij only contributes at order 2PN order in GJK. So we just need that trace, spatial trace of H to get that. And it's just, again, all we need is the lowest order piece involving tau KK. Okay, so let's look at the first iteration. And at the same time, let's keep in mind we're doing a post-Newtonian expansion, so we can throw away terms, or at least ignore terms for a moment. So at the first iteration, yeah?
How is it exactly figuring out the post-Newtonian order?
I'm sorry?
Like, to which order we have to go exactly?
Well, so it depends on the problem you're working on. So if you want to understand, say, motion of planets in the solar system, then 1PN order is good enough, because in the solar system, epsilon is typically about 10 to the minus 8, say at the Earth's orbit. It's about 10 to the minus 7 at Mercury's orbit. So, so you're making an error of order apart in 10 million by ignoring 2PN effects. Well, now, if you think about the accuracy with which we know, you can ignore 2PN effects in the solar system. Deflection of light, we'll see, is a 1PN effect. And if you consider the accuracy of things like very long baseline interferometry and deflection of light by the sun, 1PN is still adequate. In the future, one may need to think about 2PN effects if one starts getting very, very precise things. There's a phenomenon called the Shapiro time delay, which is also a post-Newtonian effect, with laser ranging to satellites on the far side of the sun. That might be so accurate, you might have to include 2PN. But by and large, and today, 1PN rules is enough for the solar system. But for an inspiraling binary system of neutron stars or black holes, it's not adequate at all, not by a long shot. And in fact, that's why we need to go to 2PN, 3PN, 4PN order to describe the dynamics there, because people at LIGO tell us to analyze the data and to get unbiased estimates of things like masses and spins, you need all these higher and higher order corrections. So it really depends on the physical context and the measuring accuracy that you have available to measure phenomena. And the other point is we're doing just 1PN order because that's all I want to do. That's all we have time for in this lecture.
How are we deciding up to which term we have to go in?
Well, yeah, well, again, so as I said, so we need H00 to just not the lowest order, that will give us the Newtonian, so we need the first order correction to H00, and so in a moment we're going to look at this. All these higher order terms, you remember they're higher derivatives, those are higher post-Newtonian order, right? at lowest order, this looks like the Newtonian potential. Well, this is whatever it is, it's got a V over c squared there, right? Time derivatives generate V, so it's got to be smaller than that by V over c squared. So that's at 1 pn. Well, look at all these higher terms, they're just 2 pn and 3 pn beyond, so we throw them away. But we still have to delve into these things and see what to keep and what to throw away to get a consistent 1 pn result. Well, so this, remember we need this to epsilon to the 3/2, okay? And this is already epsilon to the 3/2. This T, at lowest order, this is rho times Vj, right? So this is rho Vj over r, so like m over r times v. So m over r gives you an epsilon, v gives you an epsilon to the 1/2, that's what we need. And that's all we need. We don't need to go higher. And similarly, this looks roughly like rho v squared, although there's another important term that we'll get to. And that's, so m over r times v squared, that's order epsilon squared, and that's what we need for this guy. But that's all we need. We don't need anything higher than that, because that will be a 2 pn and 3 pn. Yep. Generally speaking, the higher order corrections just produce higher order corrections of the 1 pn phenomena. So in other words, at 1 pn we'll see we get the perihelion advance of Mercury. At 2 pn just adds a small correction to that, and so on. At 1 pn order we'll see that in a two-body system the semi-major axis eccentricity are constants, no secular effects, right? That will hold true for 2 pn and 3 pn as well. So generally speaking, you don't get, and this is not a hard and fast rule, but generally speaking, you don't get some brand new effect for simple problems at higher order. There are cases where you can get a new thing happening, a secular variation in an orbit element that you didn't have at 1 pn, but suddenly you get at some other order. But that happens in certain cases. If, for example, you're working at 1 pn order, but the body you're looking at has a quadrupole moment, then there are terms that involve the mixture of the quadrupole Newtonian potential of the body with post-Newtonian terms. It's still 1 pn, but you're now including the quadrupole moment. In that case, the semi-major axis does have a variation. This is just recent work that I did a few years ago. But that variation is necessary in order to conserve the total energy of the system. It's a kind of, it's just a natural variation of the semi-major axis. So in that case, there's a situation where you do get a phenomenon that, it's still 1 pn order, but you're working with a slightly more complicated system. The big thing that's going to be new when we do this post-Newtonian expansion, that you don't get at 1 pn, 2 pn, or 3 pn, is when we include 2.5 pn, that's radiation reaction, and that's going to cause new phenomena. And I know we're looking forward to those new phenomena, the damping of the orbit, the in-spiral that's produced by radiation damping. But we'll get there toward the end. I mean, we're going to revisit some of this once we've done some gravitational radiation, and we're going to look at the 2.5 pn contributions that will cause orbits to decay. Any other? Yeah.
Suppose I had the weak field approximation in place, but suppose now I had lifted the slow-moving approximation to it. Then, for example, I would have still done that expansion out there, the minus g expansion in terms of space, and retain only a specific number of terms. But could I have written these equations, or could I have, what changes would that?
Right, so So I think nothing here would change because basically I'm really only keeping, well, no, you're right. I've used the slow motion assumption in establishing this hierarchy. You don't have to do that. You could keep V completely arbitrary, in which case you would need to know all of these metric components to the same accuracy in principle. You could derive them to whatever order you wanted in post-Minkowskian theory, and then later decide whether you want to have slow motions or not. Okay, so that certainly is doable and quite straightforward. As long as you're not going to too high. Of course, in all these calculations, the higher order you go, the messier things get. But it's certainly not hard to do. In fact, in the chapter on post-Minkowski theory, we keep the velocities arbitrary, and for example, work out what I've called the 1 over c to the 4th correction explicitly. But then later, with the slow motion assumption, you can relax that, or you don't need that for slowly moving bodies. So you can either do it at the end of the calculation, once you decide what kind of system you're working on, or you can incorporate it as you go along, which is what we're going to do here. Just because you avoid generating a lot of terms that you don't need.
That expansion stays all right.
This is fine. This really is just an expansion in powers of g. No slow motion there. And the slow motion is here just in terms of where we cut those off.
So that's just the weak bit, the upper one.
Yeah, just weak. Okay, so let's first look at the first iteration for h00. So that says in here we plug in h equals 0, right? So that means the Landau-Lifshitz and the harmonic, they go away because these depend only on h. Throw those away. In T itself, the metric occurs. Remember, because there's a metric occurs in here, there's a metric, blah, blah, blah. Make that Minkowski metric, throw away the metric that's in here, blah, blah, blah. Just make it Minkowski. Throw away the metric completely. And because we're keeping in mind that we're also at the same time doing this post-Newtonian expansion, let's throw away epsilon, that's a post-Newtonian correction. Let's throw away p, that's post-Newtonian. Let's throw away all the corrections involving v, those are post-Newtonian. When you do all that, at the very lowest order, this just reduces to rho star. And again, we're going to use rho star, not rho, everywhere. And if you want, let's just keep this for the sake of argument. So that reduces to rho star. Well, we know what the answer to this is. H001, the first iteration, is just 4 g over, and I want to keep my c squared careful. There's a c squared coming from u0. So it's 4g over c squared times u plus 1/2. The g goes into the definition of u, plus 1 over 2 c squared times this superpotential with 2 time derivatives. And the superpotential is just defined with rho star. Here I'll give you the answer, but it does show the definitions of some of the potentials that we'll encounter. So there's x, the superpotential. There's u, the Newtonian potential. Okay? But remember, this is already a post-Newtonian correction, so we'll just keep it, but we could have included it later. This is the dominant correction. And we see that will give, for g00, that will give -1 plus 2u over c squared. And that's the Newtonian limit that we're after. Okay? Okay, what about this one, h0j? Again, throw away all the Landau-Lifshitz and harmonic junk, throw away the metric, let's throw away the post-Newtonian corrections. We really just need this to the very lowest order. So in this case, tau 0j reduces to rho star times vj. Right? So the solution here, h0j, 1, is 4 times uj. And uj is defined here It's just a vector potential, very much like the vector potential of electrodynamics, right? Potential generated by the mass current, just as the one in E&M is generated by the electric current. Okay? And then we have HKK1. Again, throw away all the stuff, put H equals 0 on the right-hand side. We'll throw away all the higher order post-Newtonian corrections, because again, we just need the leading term. And the trace of this, UJUK, which is proportional to VJK, is just V squared. So this is going to be an integral of rho V squared over x minus x prime. So HKK1 is equal to 4, and a potential called phi 1. And that's the potential generated by, it's kind of generated by kinetic energy, right? Rho V squared over x minus x prime. Right? I'm sorry?
The next two terms shouldn't be again power of C.
Oh, no doubt. You know, the trouble is, Eric Poisson insisted that we have G and C. I grew up under Kip Thorne, where G and C was 1, or both 1. And it, you know, I naturally think in terms of G and C equal 1, but to be consistent with the book, I've got to put it in, and so I'm going to forget all the time. So keep reminding me. So this is 4uj over C cubed, because U over C squared is dimensionless. This has a power of V in it, so you have to have V over C to make it dimensionless, right? So it has to be C cubed, and this one would be over C to the 4th, because it has an M over R, GM over R, and a V squared. So to make it dimensionless, you have to have C to the 4th. Okay. I'm sorry? Phi, it's the first term in that little psi potential, which just combines a bunch of these potentials. Phi 1 is rho star V squared prime prime over x minus x prime. But notice, this tells you that kinetic energy generates gravity. So it's not just mass, you know, all forms of energy produce gravity. So here's an example where kinetic energy. Okay, so that was the first iteration. So now we need to do the second iteration. And I'm clearly not going to go into this in detail, just kind of sketch it. So we need the second iteration of H00. Remember, we needed to get the next term here, including all the various post-Newtonian corrections. So now, in tau 00, we have to stick H1 in here. For that, we just need the lowest order one, since this is already going to be a post-Newtonian term, so we just need to stick in that Newtonian potential into this thing. So you go back to that page that showed the Landau-Lifshitz pseudo-tensor spread over 4 lines, look at all the possible terms, and you know, stare and work out and throw away terms, and ultimately you have to boil it down to a simple expression. And as I recall, what you get for tau 00 is something that looks like 7/8 times the gradient of U dotted into itself. Roughly speaking, I forget the exact coefficients, but all that junk at this particular order boils down to, I think, basically one term, and that's all there is. This actually doesn't contribute at 1 PN order at all. But of course, we have to put our H1, our Newtonian potential, into this, because it appears here, so it has to be put in to the right order. There's a minus G in the definition of tau we have to take care of. So you have to make sure it's in here. And you get an expression that looks like rho star times a bunch of corrections. There's stuff involving V squared, involving pi, involving P over rho, involving U itself, etc. So you get a Newtonian potential of stuff, of all the various variables that we've defined. It turns out that you also have to iterate this one to second, do a second iteration of this HKK. We threw away, we didn't put H into the TAW when we did the first iteration, but when you look at the second iteration, it says you stick H1 into Landau-Lifshitz, stick it into the metric everywhere else, and it turns out that the Landau-Lifshitz bit when you're looking at the ij component also contributes a term that's proportional to grad u dot grad u with another factor in front. And that is of the same order as the rho v squared term that we had in the original calculation at the 0th order. Why is that? Because grad u dot grad u, you can sort of move the gradients around, and you can show that this is equal to 1/2 times del squared of u squared plus u del squared u, but del squared u is minus 4 pi g rho, so it's 4 pi g rho times u. So that means that this term is of the same order as rho times u, but that's the same order as rho v squared that came from the velocity part here. Because remember, v squared is comparable to u in our slow motion assumption. So here, the first iteration didn't really give the right answer. The second iteration is needed to get to complete the answer to the proper order. But again, it really just comes from here. You have to look at the terms carefully, figure out what term contributes at the order you need, use this identity, which is very useful to convert this thing. I'm not sure how to calculate the potential of that. That thing over x minus x prime d3x prime is kind of hard to figure out. But you know what this is. This is going to be a potential over x minus x prime that'll look just like this contribution. That's actually called phi 2. And this, you know what the answer will be, because if you take that del squared u squared and divide by x minus x prime and integrate, you can just integrate by parts and see that the answer is just u squared, modulo boundary conditions. Basically, this integral is the inverse del squared of del squared. It's like del to the minus 2 of del squared u squared, and the answer is just u squared. So you'll get an answer from here that's proportional to the square of the Newtonian potential. Okay, so pulling all that stuff together, H00 plus all the post-Newtonian corrections, including this guy, this retardation guy, this is okay. This we have an additional term now involving this potential phi 2, which is an integral of rho prime u prime x minus x prime. Pulling all that stuff together then, you end up with the post-Newtonian metric that looks like that. So at lowest order, you have the Minkowski metric, 2u over c squared, that's the Newtonian contribution. This part we got for free. There's the vector potential in G0J. And then the post-Newtonian corrections in G00, this is the part that required the work. Well, we have our 2-time derivatives of the superpotential. That's just a reflection of the retardation of gravity in GR. This doesn't appear, of course, in Newton. There's a term that's just proportional to u squared, the square of u, and part of it came from this HKK, and part of it comes from the Landau-Lifshitz contribution in H00. They combine to produce that. And then there's this thing that just sort of gathers together all of these potentials generated by v squared, u, pi, and p. And so you get this kind of psi potential generated by kinetic energy, gravity itself, internal energy, and pressure. Pressure produces gravity too, interestingly. And there we have it. That's the 1pn metric derived using this post-Minkowski theory. Okay, any comments, questions?
Do the second iteration contribution which you initially showed. You also have the other terms of the normal chain.
Uh-huh. Yes. Right, as a second iteration, so we have to now stick the Newtonian potential into the definition of U, and notice it's going to appear there in the, in the d by d tau part. So you have to include it. You can expand it, of course, because you're working to just the next order. So it'll appear there. It'll appear in G there. Although P itself is already post-Newtonian order, so you really can just use the Minkowski metric in that part. And of course, it'll also appear in the you need to change from rho to rho star. And the metric appears in that thing too. So you have to stick it in everywhere you think it might be needed. But it's pretty straightforward to do at this order. So then that's what gives you this expression in terms of rho star with all these higher order corrections. And this Landau-Lifshitz formula, you need to exploit that identity to convert it into some terms that involve this potential and other terms that just involve U squared itself. Okay, other questions? Right, I mean, you knew that this term had to be just U, right? Oh, yes, so, well, again, since at this, we know that this is going to be a 1 PN correction, you can use the Newtonian H00 in there, and so you just need to use the Newtonian potential. If you're going to 2 PN order, you have to include, put back in higher order expressions. So going to higher order just gets, more and more, as you can imagine, it gets more and more complicated, but systematically, you know how to do it. Anything else? Every what? No doubt. Let's see. Yeah. Because two time derivatives, so two time derivatives of this looks like mass times radius, right? The way we defined it. Take two time derivatives. Each time derivative gives a v over r. So it's v squared over r squared. So this is m over r times v squared. So you have to have 1 over c to the fourth. So again, thank you. C is 1, so what difference does it make? Right? But I have learned that it helps to keep track of things, keeping C not 1. I mean, I've sort of come to appreciate keeping G and C in there. It's just that it's so ingrained. Okay, so there's our 1 PN metric. Well, given that metric, we can do physics. We can calculate equations of motion. We can look at proper distances between things. We can do lots of stuff. So that's what we want to do now, apply that thing to specific problems. So for example, there's the equations of hydrodynamics. We talked about these earlier in Newtonian theory, the Euler equations. So now we can find the analog of the Euler equations, but including post-Newtonian corrections. The simplest way to get there is just to take our covariant divergence of the stress energy tensor vanishing. You could use that other formulation of the equations of motion that I talked about, involving an ordinary divergence of that tau that includes all the Landau-Lifshitz stuff. It turns out that this is much simpler. They're both equivalent, but this is much easier. So to do this, you have to calculate the Christoffel symbols that are produced by this metric. So you know how to do that. Standard formulas for the gamma, ijk, alpha, beta, gamma. And then you plug it into the standard formula for the for this, and use our formula for the stress energy tensor, including all the corrections. You have to put the metric in here and the metric into rho, convert to rho star, u, etc. So you generate formulas for these things to the appropriate order. Combine terms, boil it down a little bit, and then you end up with this equation that looks first, on the first line is just this famous Euler equation. Rho dv dt is minus grad p plus rho grad u. Here, of course, we're using rho star because we really like this conserved density because of its nice conservation properties, but otherwise it looks just like Newton. And then there are correction terms. Correction terms to the potential gradient. These are all 1 over c squared, you can see, are all epsilon smaller. There's the term involves the rate of change of pressure times the velocity. There are terms here that involve nonlinear interactions, u times u, and the velocity of the body itself enters in. Term involving time derivatives of that vector potential. Here's a term that looks like a v cross of the curl of the vector potential, and then the gradient of that potential psi, which includes all of these other things. Oh, this is capital psi. It's that other psi plus, and I've just thrown the 2 time derivatives of the superpotential in there because it's simple. It's a gradient of them all, so it's to lump them all together. Now, if you stare at this a little closely, you might see at least a couple of, you can see 4 terms in there that if you combine them together, it's very suggestive of something. This term here, this is a vk dotted into this antisymmetric derivative of the vector potential. Well, this combination is just v cross del cross u, right? What's the cross of a vector potential in another field of physics that you know? The magnetic field. So it sort of looks like V cross B. And if you remember the formula for the electric field in electrodynamics, what is it? Sorry? What's the electric field in electrodynamics? How do you express it in terms of the various potentials? It's grad phi plus the time derivative of the time component of the vector potential. Well, look at this. Here's grad of u plus a time derivative of the vector potential. So these 2 terms look like the electric field plus v cross the magnetic field. And in some situations, especially if you're doing laboratory experiments where you want to explore various aspects of gravity, in many situations you can ignore a lot of this other stuff, and these terms actually dominate the problem. And so people have gone so far as to call this gravitomagnetism, because of the analogy with ordinary magnetism. The acceleration, it looks like E plus V cross B. Notice one key difference between this and E and M is the factor of 4. Here the relevant vector potential is 4 times the potential generated by the current. Whereas in E and M, it's just the potential generated by the current. We've got this extra factor of 4. It's related to the fact that basically gravity involves a tensor field, whereas E and M involves a vector field. It's probably related to that. Maybe 4 is just is the spin of the field squared or something? I don't know. Gravity is always associated with a spin 2 field. I mean, no one has thought about this any more deeply, but this gravitomagnetic analogy is sometimes useful in certain kinds of problems. But of course, the full hydrodynamic equations are there. There are lots of other correction terms that in principle you need to include. And now I want to take these and attack a number of specific problems. And the first one I want to attack is a repeat of the calculation that we did in Newtonian theory. The motion of n bodies moving around each other, each body treated as a very, very small compared to the distance between them. Bodies that are isolated, so there's no mass flow. We ignore tidal. Here we're going to ignore all tidal contributions. In Newtonian theory, we included all those multiple moment contributions. Here we're going to ignore them. To include them would get very, very messy. So we're going to really treat our bodies as almost point masses, very, very small, ignore their finite size as much as we can. Turns out there's a simple assumption that really makes a lot of calculations easy. We assume our bodies are reflection symmetric. So in other words, you take any plane cutting the body, and the body's the same on opposite sides of the plane. So that's certainly true for a spherically symmetric body, true for an axially symmetric body. It's actually true for a tidally deformed body, simply because perfect fluids tend to settle down into these kinds of relatively symmetric conditions. Would mean, for example, that all the multiple moments, if there were any, would be of even order. Now you might say, wait a minute, the Earth has odd multiple moments. There's an L equals 3 moment for the Earth. Well, that's because the Earth is not a perfect fluid, right? The Earth has a rigid crust and all kinds of things that are not perfect fluid that can support, deformations of all kinds of shapes. But the kinds of perfect fluids we talk about tend to settle into relatively symmetric states. So we don't have to assume perfect spherical symmetry. This is enough to, simplify the calculation that you have to do. And here's why this rho star quantity is so beautiful. We can now do everything we did in Newtonian theory in exactly the same way. We need to define a mass of each body, defined this way, center of mass of each body, a velocity of each body, and an acceleration of each body. And because this rho star satisfies a continuity equation in our coordinate system, these things are very nice. And again, this is completely conventional. This is the convention I've chosen, but it works and it makes life simple, and so it's a good choice. But it's not unique, again, have to emphasize. And just as before, we this would be the center of our coordinate system. We look at any point inside each body. We expand that in terms of the distance to the center of mass of each body, plus a small vector within the body, and then we have to integrate the hydrodynamic equations over each body. So we take all these potentials, expand them about the centers of mass of each body, but we have to do a bunch of integrals within each body to get the full equations of motion. And it turns out that when you do that, you get some surprising terms that you wouldn't have gotten in Newtonian theory, because these are all post-Newtonian terms. You find, for example, that the acceleration of a body might depend on the kinetic energy inside the body. And here's an example of exactly such a term. Suppose I take this thing and integrate over body A to get the acceleration of body A. Well, here's a term that involves rho v squared, this is in body A, times the gradient of the potential. Let's suppose this is the potential from the other bodies. So I have a term in the acceleration, mass times the acceleration, that looks like integral of rho v squared over body A times the gradient of the external potential due to all the other bodies. Okay? Well, you might say, well, I'm worried about that because I thought the equivalence principle holds, and this says that maybe the kinetic energy of inside the body may affect its motion. You can also get terms involving the internal gravitational energy of the body. Here's another one. Suppose we're integrating over body A, so rho star, and suppose we look at the A, this is all the potential due to all the bodies, but let's look at the potential just due to body A. So the integral of rho star UA times the gradient of the external potential. So that's a term that looks like rho prime over x minus x prime, d3x prime. That's rho, that's u inside body A times the gradient of the external potential. So again, you might worry, oh, what's going on here? And even worse, if you let your body get smaller and smaller and smaller, this term is going to blow up because x minus x prime gets smaller and smaller. This term will be sort of singular in the test body limit, right? So that's even worse. So what's happening here? This is a complete breakdown in what's going on. Well, you carefully calculate all such terms. These two are pretty obvious, but throughout this calculation, terms like that arise, and you have to very carefully do these expansions, keep track of all the terms, and you discover that there's lots of terms that involve the internal energy of the body. This is the kinetic energy, like that. This gravitational potential energy, it's defined to be negative, of course, because it's attractive. So there's this internal gravitational energy. There are terms that involve just the integral of the pressure over the body and terms that involve the internal energy of the body. And these terms are all over the place. And you say, oh my God, what's going on? Especially since these terms blow up when the body gets smaller and smaller. But then you discover there's an important theorem in Newtonian theory that you can exploit. It's called the virial theorem. It says for any bound body, that is, you can make the conditions a little more precise, but basically any bound body, this is satisfied. 2 times the kinetic energy plus the gravitational potential energy, notice it's negative, plus 3 times the pressure vanishes. You get this from the Euler equations by calculating the second time derivative of the moment of inertia tensor, and then letting that second time derivative vanish because you have a body that's more or less in quasi-static equilibrium, so any time derivatives are very small. So if you have a body in this kind of quasi-static equilibrium where it might change only adiabatically in time, then those 2 time derivatives that are on the right-hand side vanish or are very small, you set them to 0, and so you have this very important relationship. And you can use this here because we're talking about post-Newtonian terms. This is only valid in Newtonian theory, but since we're only going to use it in post-Newtonian terms, we're okay, because any errors we're making will be of second post-Newtonian order. Now, if you want to go to second post-Newtonian order, you have to worry about those corrections, but here we don't. So we can look at these terms that involve t and omega and see what happens if we pull them together and combine them. And when you do that, a miracle occurs, and everything cancels. All these terms cancel because of this relationship, except for a few. But those terms that don't cancel always occur in expressions where you can take the original mass that we had for the body, the integral over rho star, combine it with this plus this plus this, and that combination occurs in every term at post-Newtonian order. So, but what is this? This is the mass plus the kinetic energy plus the potential energy plus the internal energy of our body. It's really, that's the total energy of the body, including all the other forms. So, the equations of motion simplify in such a way that the mass that occurs is not just this baryonic mass or the rest mass, it's actually the total mass, and that occurs systematically, and so you can renormalize the mass into a new mass, ma, that is the true mass of our body. For finite bodies, this is fine. If you were worried about our bodies being, letting them get smaller and smaller so that something like this blows up, well, since you can renormalize every mass in exactly the same way, that doesn't matter. And we know that there's no such things as point masses in reality. All bodies have finite extent. But here, the internal structure doesn't matter. Only the total mass now matters. And this, you can see when you write down all these post-Newtonian equations, all the terms that involve these things either cancel each other through this, leaving a residue of terms that can all be combined together with the original mass to be renormalized into a new one. And this is a manifestation of what's called the strong equivalence principle. It apparently, as far as we know, is satisfied by GR and only GR. Most alternative theories of gravity violate this principle, including the famous scalar tensor theory of Brans-Dicke and others. And what we see from this calculation is that all bodies fall with the same acceleration, independent of their internal structure. It depends only on their total mass energy, even bodies that have internal gravitational energy. Remember earlier we talked about the weak equivalence principle, where bodies fell with the same acceleration independent of nuclear energy, weak interaction, E&M energy. But now with general relativity, even with internal gravitational energy and all these other energies, the bodies fall with the same acceleration. Acceleration only depends on the total mass. Well, the acceleration itself doesn't depend on the mass, but only total mass is relevant. Now, of course, this is all done in the weak field limit, and you can actually show that this is valid to second post-Newtonian order. It's valid to 1pn. It's a little harder to prove it to 2pn order, but you can do it. This was done some years ago by Grischuk and Kopeikin, and later on in a slightly different version by my student Tom Mitchell and me. So at 2pn order, you can show it explicitly. You can really show that these higher order terms just go away and can all be absorbed in a well-defined way. And so it suggests that the motion of all bodies is independent of their internal structure, including neutron stars and black holes. Now, of course, our calculation can't tell us anything about black holes because black holes aren't made of perfect fluid. There are a few calculations that have been done, notably by Peter Death and others, in very specialized circumstances that show, for example, that a black hole, the acceleration of a black hole in an external field is given just, that doesn't depend on its mass at all. So we don't know for sure if this is valid at all orders and for all cases, but at least certainly through high post-Newtonian orders, we know that it's true. Okay? Any questions? Yeah. Well, it's an approximation because this is valid in Newtonian theory using the Newtonian equations of motion. But we're only using this in post-Newtonian terms. I mean, the Newtonian term is trivial, we know that, that's simple. So since we're only using it in post-Newtonian terms, any error we're making will be of second post-Newtonian order, right? So the way of saying it is this, technically speaking, this is not zero, it's of order epsilon. Okay, but we're sticking this into a term that is already of order epsilon squared, so the error term will be something of order epsilon cubed. And that's 2pn order, which we don't have to worry about. Well, this is what Tom Mitchell and I did. At 2pn order, you have to, there are many, many similar such potentials at 2pn order. You have to worry about the 1pn correction to that. You also have to worry about the fact that we assume spherically symmetric bodies at 1pn order. At 2pn order, you have to worry about the fact that a body that's symmetric in its own rest frame is no longer symmetric in a frame through which it's moving because of Lorentz contraction, and that actually changes things, introduces its own corrections to the virial theorem. So, as again, when you go to high orders, you really have to sweat a lot of details. There's no evidence one way or the other beyond 2pn order. So in particular, at 3pn order, where we have all these equations, and even now approaching 4pn order, the method that's used is quite different from this. The method, they use point particles right from the start and use very fancy regularization techniques to deal with the fact that for a point particle, such a thing is infinite. And they use very sophisticated regularizations to handle those problems. So at 3pn order, for example, we simply do not know if this is true. Well, the point is, in this calculation, we never had singularities. We were always dealing with nice finite fluid bodies. So you can renormalize this, and all that matters is the total mass. So as long as your body has a finite total mass, including its internal energy, these are the results apply. But since we know point masses don't exist, I mean, it's kind of a moot point. The point mass that people use is simply a calculational tool to get around having to deal with finite balls. I mean, it gets very, very complicated at high PN orders to really deal with finite-sized objects. So there's a trade-off, when you go to high orders. Well, there's the answer. So these are the n-body post-Newtonian equations of motion. So there's the acceleration of body A, given by first the Newtonian term. It's just the standard acceleration due to body B, mass of body B. This, of course, is the total mass, including all those internal energy terms for body B, which would be of post-Newtonian order, but we can absorb them into MB. 1 over r squared law, unit vector pointing from body B to body A, so it's a minus sign. But then there are post-Newtonian corrections. There are corrections that are along the line joining the two bodies, but we see velocity of body A and B both enter, VA dot VB, some complicated thing there. Notice that the potential produced by body A enters in. So the gravitational potential that body A produces affects its own motion. It curves the space-time around it in such a way that acts back on it to move itself around a little bit. And of course, there's a potential due to body B. This is just a non-linear effect of the gravity due to body B. There are terms that are in the directions of the velocities. So the acceleration is no longer radial. There are terms that are in the direction of the velocities. And there are terms here that are three-body terms. This is a sum over B not equal to A and over C not equal to A or B. So the acceleration of body A is affected by a combination of the fields due to body B and body C. Again, this reflects the nonlinearity of gravity. You know, gravity generates gravity. So the gravity of body B and the gravity of body C combine to produce an effect on body A. And there's even a term here where the acceleration of body A is in the direction of the line between body B and body C. So again, just gravity is nonlinear, so you get these nonlinear effects. These are often called the EIH equations of motion after Einstein, Infeld, and Hoffman, who derived them in around 1938 by actually solving the vacuum Einstein's equations. It was a very clever approach where instead of using any kind of fluid or matter, they solved the vacuum equations in a very general way for the sort of the region in between all the bodies. They treated each body as kind of a Schwarzschild metric, a spherically symmetric body, and then matched the metric in a region surrounding each body using a matching technique. And that matching technique worked only under certain conditions, and the conditions under which it worked was that each body had to move according to those equations. It was today we would call it the method of matched asymptotic expansions, but it was a very, very clever work. Actually, though, the equations were derived earlier by a young student of Lorentz called Droste, who did a method somewhat similar to this and derived these same n-body equations. They're also derived by Willem de Sitter, but he made a mistake. He actually missed one of the terms in here, one of the highly nonlinear terms, so his equations were actually in error, but that was corrected later by someone else. Chandrasekhar derived these things, Fock, various other people using this hydrodynamic approach, so there's a long history to deriving these n-body equations of motion at 1pn order. But of course, we've now gone beyond 1pn, 2pn equations have been derived. They were derived quite some time ago. Then 3pn, and now the work is sort of converging. Two different teams are working on the 4pn equations of motion. There's some slight disagreements in their results at the moment that they're trying to resolve, but hopefully we'll have those set. And then later on, toward the end, we'll worry about the corrections at order c to the fifth, 1 over c to the fifth. These are the 2.5pn terms. These are the ones where gravitation-radiation reaction enters in. Okay. So just to summarize our post-Newtonian calculation, we've derived the metric to 1pn order in terms of a series of potentials. They all look like Newtonian-like potentials. They're all simple solutions of Poisson-type equations, just an integral of 1 over x minus x prime, but the source can be the density in the Newtonian potential, kinetic energy, gravity, internal energy, pressure. There's a superpotential that occurs. That reflects two time derivatives of x. That reflects the retardation of gravity. And then there's a vector potential that appears in G0J. Okay? So what I want to do after the break is take these equations and apply them to some other situations. A geodesic equation for just a test particle moving in some post-Newtonian field of a source. And we'll talk about the motion of light and other phenomena for which we can use this 1pn metric.